The question I have is, could you do an example on the calculation of nail spacing in built-up beams? And in this example, I will consider beams with three different cross-sections, which are somewhat complex, not very complex. So here are the three sections that I want to consider. These beams are constructed out of boards by fastening them together by nails at a spacing of S, and we have a value for S. S is 10 millimeter. It's given that each nail can resist a shear force of 1.2 kilonewton. The question is to determine the maximum shear force V that the beam can support without causing shear failure of the nails. The first steps in solving problems like these are, number one, to calculate the location of the centroid, number two, to calculate the second moment of inertia about the z-axis, right? Both of these are given to us. In another video, we covered the details of how we connect the nail spacing little s to the shear floor little q. Just in case you haven't seen that video yet, I'll leave the details of the theory here. So here is the connection. All right, so F over S equals little q, which is VQ over I. F here is the strength of a single nail, and S is the nail spacing. Now, whether we use the full little q or half the q or 1/3 of the q depends on the way the boards are arranged in the cross-section. Let's go ahead and calculate q for these sections. We are interested in designing the nails, and if the nails are going to fail, they're going to fail by shearing along these horizontal planes, right? And therefore, we need to calculate the shear forces on these horizontal planes. So that tells you the shaded area to consider. So in this case, the shaded area would be this right there. Q then is A prime times Y bar prime. A prime is this distance multiplied by this distance. Then this distance is 650 millimeter or 0.65 meter multiplied by this distance, which is 50 millimeter or 0.05 meters, and multiplied by Y bar prime. Y bar prime is the distance, the centroid of the shaded area from the z-axis. So that's this distance right there. So that'll be 126.6 millimeter minus half of this distance right there, right? So that'll be 25 millimeters. So that converted to meters is what I have over here. So Q is calculated to be 3.31 times 10 to the minus 3 meter cube for this section right there. So here are the details of the calculations for the maximum shear force that the section can withstand. Firstly, we notice that there are two rows of nails, and therefore the shear floor per row would be little q over 2, and therefore F over S must be equal to q over 2, which is VQ over 2I, and from this we get this equation for V. Now we substitute numbers, so it will be 2 times F is 1.2 kilonewton, which is the strength of a single nail, right? And I is 0.9222 times 10 to the minus 3 meter to the power of 4. Q, we just calculated that to be 3.31 times 10 to the minus 3 meter cubed. And S, spacing, was 10 millimeter, right? So that's 0.01 meter. And that gives us a maximum shear force of 66.85 kilonewton. Here are the details of the calculations for this section. Here I am considering this shaded area. The calculated shear flow would then be the force on this plane and this vertical plane. In other words, F over S must be equal to Q over 2, just like the first case. Now you can follow the numbers very easily, so I'll let you do that. Now in the third case, there are two possibilities for the failure of the nails. They can fail on these horizontal plane. This row of nails and this row of nails are subjected to the same force. Or they can fail on this vertical plane. Again, this row of nails and this row of nails are subjected to the same force. In both of these possibilities, there are two rows of nails, and therefore this equation that we have developed for the first two cases is still applicable. But this time I need to calculate the maximum force that could be applied on this section on the basis of the failure of nails over here and here separately. So that's exactly what I have done here. For the first possibility, this is my shaded area, and the area of the shaded part is A1 prime, and the distance, the centroid from the z-axis is y1 bar prime, right? So you multiply these two, we get Q1. All right, so using Q1 in this equation, I get a value of 77.35 kilonewton for the shear force. So let's call that as V1. For the second possibility here, the shaded area that I have considered is this part right there. So Q for that would be A2 prime, which is the area of the shaded part, multiplied by y2 bar prime, which is this distance, right? That's the distance to the centroid of this from the z-axis again. So that's exactly what I have done here. So I call that Q2. And using Q2 here, I get a value of 187.4 kilonewton for the maximum shear force that can be applied. So I call that as V2. So if I don't want the nails to fail anywhere, the maximum shear force should not exceed the minimum of these two values. So the maximum shear force that can be applied, therefore, on this section is 77.35 kilonewton.